The idea that the universe is evolving is quite recent in the history of science and of cosmology. Cosmology is interested in the evolution of the whole universe, is interested in properties which characterize not one part of that universe, but of this global object itself. Cosmology has evolved during the centuries from the Greek antiquity and of course before up to now, with many changes. It is interesting to look at the way that our predecessors were looking at the world, and this was of course very different than our present knowledge. And for instance, in the Greek antiquity, they already had a geometrical representation of the world, and that's a very important thing, because the fact that we have to describe the world with geometry has been a constant about 2 millenniaries in the Western civilization. They had not what we call now cosmological models, but they had some descriptive geometrical system that we call système du monde. And the difference is that now we have cosmological models which try to not only to describe how goes the world is going, the universe, but to explain how it works, to explain based on the physical laws that we know. And the world system of the Greeks, for instance, were only descriptive. And of course the world as they describe it was very different, because we had the Earth at the center. We have only spherical or circular motions and spheres everywhere in the sky. We have a hierarchical structure of spheres around the Earth, and a combination of circles which were called epicycles to explain the motion of planets. This is more or less the way that Plato and Aristotle described the world, and I will not go in more details, but this is just to mention how it was different from now. So you had a center, you had a hierarchy of spheres, and you had a border to the world. The world was finite, very small, and with a border. And of course this notion of border was very problematic already at that time. And it is interesting to see how this notion of a possible border and the finite or infinite character of space was a constant preoccupation during these 2 millenniaries, and how it is solved now I will tell you in a moment. So you had a big change at the Renaissance in the 14th, 15th centuries, and of course you know the name of Copernicus, and the great achievement of Copernicus was to understand that the center of the world was not the planet Earth but was the Sun, and he moved the center from the Earth to the Sun. And I think the important thing was not the point that the center was moved, but the point that the Earth was considered as mobile, not at rest. And if you are in a planet which is moving with respect to other planets, it's much more easy to understand the very complicated apparent motions of the other planets, because apparent motion is a combination of the real motion of the planet and the motion of the observer, which is on the planet Earth. And this was a big achievement of Copernicus, but of course this was not the end of the story, and you had very nice contribution of Kepler, but I won't go into the details. And Kepler was convinced of the harmony of the world, and harmony of the world was a very important subject which was already mentioned by Pythagoreans, by Plato, also by Kepler, later by Einstein. And this is why I mentioned this point, because it it is also present in the contemporary physics and in the contemporary cosmology under the form of symmetries, for instance, and physical laws. I will not go into these details, but you should retain that our conception of physics, astronomy, cosmology is impregnated of the idea of the harmony of the world, and of course this is more a subject for philosophers than for physicists or scientists, but I think it's an important point. So we had a big Newtonian revolution in the 17th century, and this is also a new astronomy, a new physics, a new cosmology, and the main revolution is that Newton introduces the notion of absolute space and absolute time, which constitute the frame for physics, that every event, every process is played into this frame, which is space and time, and he is describing the physical space with the mathematical space, which was known at that moment, which is Euclidean space, that all of you know very well, because that's a space, that's a geometry that we learn in school. And Newton had no choice, of course, because at his time this was the only geometrical space which was known, and this was only in the 19th century that other spaces, non-Euclidean spaces, Riemannian spaces, were discovered by the mathematicians. And you know that there's non-Euclidean spaces are at the foundation of the theory of general relativity, and general relativity is also at the foundation of our present cosmology, which is relativistic cosmology. And I will speak about that later. So you have many important improvements, and another is that Newton is identifying the gravitational interaction, and important point is gravitation is called universal, gravitation universelle, universal gravitation, and this is the first time in the history of science that we have a universal interaction. And the word universal is very important, because this means that we live in a universe where everything is united. Universal law is a law which applies everywhere on the Earth, in interstellar space, on the Moon, everywhere in the world. And this was really very new, because before the world, it was thought that the laws of physics, the composition of objects were completely different on the planet Earth and elsewhere in the universe. So this is, I think, the main achievement of Newton, to have the notion of universality, to have this notion of universe which is unique and unified, and which is the framework for physics. And of course this is very important for cosmology, because if we have a universe which is a well-defined entity, this means that this universe should have universal law, and the subject of cosmology is to discover what are the laws concerning the universe itself as a whole. And of course, what is governing the evolution of the universe as a whole is precisely gravitation. This is why the Newtonian revolution is very important. The things are going, of course, further, and in the 20th century we had also a big revolution, and this was initiated by the special relativity theory in 1905 by Einstein. And the advent of special relativity, which was the first step of the relativistic revolution, because relativistic revolution is, for my opinion, in three steps. 1905, it is special relativity, 1915 is general relativity, and 1917 is the birth of relativistic cosmology. So you have three steps. I'm speaking about the first step, which is special relativity, and special relativity was introduced by Einstein to resolve a very strong crisis in the physics of the 19th century, which was the fact that the velocity of the light remained completely constant, which means that it was not obeying the rules of the Newtonian kinematics, and this was perceived by the physicists of that moment as a big conflict, which was resolved by the theory of special relativity by Einstein in 1905. And the main message of this theory is that the notion of space and time, which were introduced by Newton, are not valid in physics, have no reality in the physical world, and should be replaced by a different entity which is called space-time. And so if you want to resume special relativity in one sentence, this is the replacement of space and time by space-time. And I have no time to detail what is the exact meaning of that sentence, but this is the main achievement of special relativity. And the defect of special relativity, as it was felt by Einstein himself, is that gravitation is not in the theory, is absent in the theory. And Einstein was very concerned with gravitation for different reasons. And after special relativity, he was very concerned and even obsessed by the necessity, the requirement to introduce gravitation into special relativity. This will take 10 years of hard work from Einstein and give the theory of general relativity in 1915. And the theory of general relativity retains the main message of special relativity, which is that the frame for physics is not space and time, but space-time. And the new thing is that the space-time has a shape, that it has a shape which is described mathematically by its curvature. And the main message of the general relativity is that the curvature, the mathematical curvature, the geometrical curvature of space-time is exactly what the physicists call gravitation. So the physical gravitational interaction is assimilated to the geometrical curvature of space-time. This means that on one side you have an equation, the fundamental equation of general relativity, which tells you how the curvature of space-time is imprinted by the material content of the universe. The material content of the universe is matter, radiation, energy, whatever the universe contains. So the Einstein equations tells you how to calculate the curvature of space-time if you know the material content. For instance, if you know the position of the sun and the mass of the sun, you are able, using that equation, you are able to calculate how space-time is curved in the solar system by the mass of the sun. And on the other side, the theory tells you also how the matter will move in the curved space-time. And for instance, if you have a free particle, if the particle is free in the non-relativistic theory, you know that a free particle is moving following a right line at constant velocity. This is called the principle of inertia. But if space-time is curved, you have no straight line in space-time. And the notion of straight line is replaced by a more general notion which is called geodesics. So the theory tells you also that free particles, and in particular light, is following the geodesics of space-time. This means that space-time is curved, and everything which is contained in space-time, for instance particle or light, will follow the curvature of the space-time. And there's two requirements: how the material content is curving the space-time and how the material content is following the curvature of space-time. These are the two main messages of general relativity, and all the rest is a calculation. There is also an important point that, as I told you, the Einstein equation allow you to calculate the curvature from the material content, energy, matter, which is described by a specific tensor mathematically, and also a constant which is called the cosmological constant, and which is written lambda. And it is important to retain that because I will speak about that later. And of course, this equation allows you to calculate the evolution of the universe itself as a whole. And the universe, of course, when you are interested in cosmology, the universe as a whole, you will not retain all its details. By details, I mean the planets, the stars, the galaxy, which are small inhomogeneities in the universe, and you will consider the universe itself as a whole as homogeneous. This is exactly like in the first approximation. The planet Earth, you will say it is spherical. Of course, this is not exactly spherical because you have mountains and valleys. But as a first approximation, the Earth is spherical. And as a first approximation, the universe is homogeneous, so it has a shape. Not a spherical shape, but it has a shape, and the main goal of cosmology is to know what is the shape of the universe. For instance, is it finite or infinite? Is it expanding or not? And in fact, when you say that the universe is expanding, for instance, rather than static, this is a point, this is a particular detail of the geometry of space-time. Because when you say in the usual language that space is expanding, in fact this is part of the geometry of space-time. And the language of space-time is very specific because it allows you to consider what in the usual language is evolution, to consider it as a part of the geometry of space-time. You have a different language, and this language is very powerful because it allows you to consider, for instance, cosmology in a very different way. And in 1917, Einstein realized that his new theory, the general relativity, was very convenient to describe the evolution of the universe itself as a whole. And the point is that what drives the evolution of the universe as a whole is really the gravitation, because you have no, for instance, electrical or magnetic interaction between the galaxy, but you have, of course, gravitational interaction. And the evolution of the universe is described by gravitation, but gravitation is quite a complicated interaction because it is described by the Einstein equation, and it is not so easy maybe to solve these equations, not maybe, certainly, except that for the universe, given that you assume that the universe is homogeneous, so the equations are much more simplified. And the complicated Einstein equations, when you make this approximation of a homogeneous universe, become Friedmann equations, which are a simplified version of the Einstein equations, which are adapted to the cosmic evolution, to the cosmological evolution. So if you want to make cosmology now, you have to solve the Friedmann equations. And for instance, a big novelty of the relativistic cosmology is that it allows something which is very new, I mean expanding universe. What means expanding universe? It means that if you have space, for instance, the surface of this sphere here is representing sphere, is increasing with time. So if you have 2 points, let's say 2 galaxies which are fixed in the universe, they are not really moving because they are fixed in space, but space is growing, is inflating like a balloon, and so the distance between the galaxies is increasing with time, and this is what we call the expansion of the universe. And you can represent this expansion by a scale factor, which represents typical length in the universe, and this length factor is growing with time. So in this plot, this is time, and this is the scale factor. And what we know from observations, I will come to that in a moment, is that now, at the present moment here, the universe is expanding, which means that the shape of the evolution of the scale factor is positive. But of course, we know that point. This means that the expansion can be eternal, or it can stop at a moment in the future and come back to a contraction, and the universe could arrive to a big crunch. And there is something that we know also from the Einstein equation, or for the Friedman equation, is that we think that gravitation is always attractive, and I will come back to that point in a moment. And if gravitation is always attractive, this means that due to its own gravitational interaction, the universe is attracting itself. And this tends, of course, to slow the expansion, to decelerate the expansion. So from this idea that gravitation is attractive, we expect that the expansion is slowing. And telling that the expansion is slowing means that this curve should have such a concavity. And if the curve is always concave like that, this means, of course, deceleration of the expansion. And just by very simple geometrical arguments, this means that somewhere in the past the curve should go to zero, like that. And when you say that the curve goes to zero, this means that at some moment in the past, at a finite time in the past, the universe, the size of the whole universe, of the whole space, should tend to zero. And this is the idea of the Big Bang. I will come back to that in a moment. So this is Einstein, and Einstein, as I told, is the first to propose a cosmological model in 1917, and he was applying his own theory of general relativity to the universe itself. And in 1917, the expansion of the universe was not known, because the expansion of the universe was observationally shown by Hubble in 1929, and it was recognized by Georges Lemaitre, which is a Belgian physicist, maybe less known than Hubble, but Georges Lemaitre is really the father of the idea of expansion and of our present cosmology. This is Georges Lemaitre. And so in 1917, Einstein proposed the first cosmological model, which is called Einstein model, of course. And since he was not knowing the expansion of the universe, he was proposing a static model. And of course, later, this static model was abandoned because the expansion of the universe was observed. But historically, this is the first relativistic cosmological model. And the same year, this was another cosmological model which was proposed by a Dutch astronomer and physicist, which was called Willem de Sitter. So in this year we had the two first cosmological models, one by Einstein and one by de Sitter. And the de Sitter model was very interesting for mathematical reasons. I will not go into the details, but it has a defect, is that it was effectively a solution of general relativity, but it was a solution without any source. This meant that the de Sitter model was describing a universe without any matter, without any energy, without any radiation. And of course, since we know that matter is here, this model was rejected. And the situation in the first decades of the 20th century was that we had two models to describe the universe, and when observation became available telling that the universe was in expansion, it happened that this could not be understood in the frame of the Einstein model, because the Einstein model was static, and in the De Sitter model, this model was empty, without any matter, so nobody could think that this model was good to describe the real world, because we observe that matter is present. So this was really a crisis in the year 1930, because people understood from observations, they were very convincing observations by Hubble, by Vesto Slipher, which was an American astronomer, and other people establishing observationally the expansion of the universe, but it was no theoretical context to understand that expansion. And the answer was given by Lemaitre, and in fact, when the expansion became known from the scientific community in 1929, it was realized that in fact Lemaitre had published a paper 2 years ago in 1927, and in that paper he was calculating new solution of the theory of general relativity, and he was showing that these solutions were predicting the expansion of the universe, and he presented some data, and he showed that the data concerning distances and velocities of the galaxy, data which were coming from the observations of galaxies from other astronomers, and that this data confirmed his model, and this Lemaitre model was recognized in the years 1930 as giving a good description of the expansion of the universe, and this was the moment where this expansion was recognized as an established fact, and this was the beginning, the real beginning of our contemporary cosmology, of our relativistic cosmology. So this year 1930 is very important. So the expansion was recognized at that moment, and it was very well interpreted by Lemaitre, but this was only the beginning of the story of our contemporary cosmology, which became very soon the story of the Big Bang models, because the reasoning was quite simple. It was made by Lemaitre in these years, and well, the universe is expanding, which means that if you take a volume of the universe containing matter, this volume is increasing, but still containing the same quantity of matter. This means that the matter is diluted by the expansion. So expansion of the universe implies dilution of the content. So expansion implies dilution, and in physics the physical laws tell you that when matter is diluted, it is also cooling. So expansion implies dilution and cooling. So the universe is expanding, its content is diluted and cooled. This means that if you go in the past, the content was denser and it was also hotter. And this was the main idea of Lemaitre, that in the past the universe was denser and hotter. And this is a basic of what we call the Big Bang models. So how more dense and how more hot the universe was in the past? So to know that, you should solve the Einstein equation, you should know the physical content of the universe, and you should apply the laws of physics, thermodynamics, radiation, electromagnetism, and so on. And when you do that, from the present observations, you manage to have a reconstitution of the past evolution and the past content of the universe. And in that way, you reconstruct the story, the past history of the universe, and this is exactly what cosmology is doing now. So what we call the Big Bang models are exactly the description of this past evolution of the universe, and it happens that we are able to reconstruct this evolution during about 13.7 or 8 billion years. And so the story of the universe is the evolution of this universe during that period of time. The title of my contribution here was The Origin of the Universe, but I will not speak about the origin of the universe because this is something we don't know. Because when you look at this reconstitution of the past, you see that when you go in the past, the universe was more and more dense, more and more hot, and a billion times hotter and denser than now. And when you go far in the past, you arrive at some physical conditions where the universe was so dense and so hot, so concentrated, that it is escaping to the evolution, to the description by our present laws. This means that our present laws of physics, I mean quantum physics, general relativity, atomic physics, nuclear physics, electromagnetism, do not apply when the physical conditions are too dense or too hot. This means that when we make this reconstitution toward the past, at some moment the physical conditions are so different than the present conditions that we are unable to describe what happened at that moment, because we have a mixture of quantum effects and gravitational effects that we are not able to describe. And this time is called the Planck time, the Planck era. And the Planck era is not the beginning of the universe. This is the beginning of the period of the universe evolution that we are able to describe with our theories. This means that before the Planck time, we have absolutely no idea of what happened, because we know that we have very strong gravitational effect, because the universe is very condensed, is very dense, so the curvature of space-time is very extreme. And at the same time, since the universe is very hot and very concentrated, we have quantum effects. But now the quantum theory and the general relativity are incompatible. They are very different mathematical descriptions. They are making very different assumptions. For instance, as I told you, in general relativity, especially when the curvature of space-time is high and in these conditions, it is impossible to define something which corresponds to time. So you have a description where it is impossible to introduce the notion of time. And on the other side, if you want to make quantum physics, you need the notion of time, because this notion is mandatory to make quantum physics. So you have in a situation where you have both quantum and relativistic effect, and you have no way to have to reconcile the two theories, and so it is impossible to make physics because we have no physical theory which incorporates both gravitation and quantum effects. Of course, theoretical physicists are trying to find such a theory of quantum gravity or a unified theory, but Einstein himself was claiming that it was necessary to find such a theory, and he made the first work in that direction. And now there is about 1 century that physicists are searching for a unified theory, grand unified theory, theory of everything, you have many names for that, which could incorporate both gravity and quantum effect. And we have no idea what could be such a theory. At some moment, people were thinking that string theory could be the answer, and well, this has been more or less abandoned now. There are ideas of quantum gravity which are worked presently, which are very interesting, but we have no answer. So for the moment, we are completely unable to describe what happened at the Planck time and even before. So the Planck time, the Planck era, I repeat, is not the beginning of the universe, but is the beginning of the history of the universe we are able to speak about. And we don't know what happened before. This is the beginning of our description of the history. And this is what we call the Big Bang model. Planck era is not an explosion, is not a Big Bang or something that you can describe like an explosion. And the term Big Bang is not adapted because it suggests an explosion which is not the good idea for that. But, well, the Big Bang is the history from the Planck time up to now. And this history has many important steps, and if now I try to expose you this history in the real chronological time, we have to start from the Planck time, and at the Planck time itself we don't know how was the universe, because space-time itself should have been in some sort of quantum state, and presently we don't know what is the quantum state of space-time. What could be a quantum state, a quantum space-time, a quantum space, quantum time? We don't know what this is. But so this should have been the situation at Planck time, and it should have been a transition between quantum space-time to ordinary space-time, the space-time of general relativity. We don't know how to describe this transition, but this is the beginning of the story we are able to speak about. And after the Planck time, so you should have ordinary space-time, or general relativity, with a high curvature. The material content was very dense, very hot, very energetic, were very concentrated, and in expansion. What is the origin of expansion? We don't know, but we know that even at the beginning of the story we are able to consider, the universe was already in expansion. We don't know the origin, but we know that it was in expansion, so it was also diluting and cooling. And at that moment, the energy was so great that it was impossible that any structural object was present. For instance, even atoms could not have been present because the energy was so high that objects were always colliding. And if an atom, for instance, was present, it would have been immediately destroyed by collision of all very energetic particles. This means that at time the universe was only some kind of soup, primordial soup of elementary particles. Only the most elementary particles were present in very high density and in very high energetic excitation. What are these primordial elementary particles? Well, they are electrons, photons, quarks, which are the constituents of protons and neutrons, and neutrinos, for instance. Only very elementary particles, and which at the present state of our knowledge are those that I mentioned. Maybe we will learn in 10 years or in 1 century that quarks are not elementary particles, but they are themselves made of more elementary particles. But today, what we think is that the elementary particles are, as I told, electrons, neutrinos, quarks and photons, and some other which play a less important role in the story. So we have this primordial soup of particles without any structure in it, and slowly this is expanding, this is diluting, and this is cooling. And the idea is that when the universe is cooling, gradually some structure will appear, more and more elaborated structure. So first we have only very elementary particles, then we will have some less elementary particles. I mean that, for instance, at the beginning we have only quarks which are not linked to other, and at some moment the quarks will link 3 by 3, and you know that protons or neutrons are structure linked structure of three quarks which are linked. So at some moment from this soup of quarks we will have a transition to the more elaborated particle which are protons and neutrons. Protons and neutrons belong to a family which is of particles which are called hadrons. Hadrons means heavy particles. So this step in the evolution of the universe is called the quark-hadron transition. And this happened very early. This happened in the first microsecond after the Planck era. So after that we have a universe which is full of protons, neutrons, neutrinos, electrons, photons, and other particles which are not very interesting for our story. And this soap is continuing to expanding, diluting and cooling. And the next step in the structuration will be that some protons and neutrons will interact to form a basic structure which are some elementary nuclei. You know that an atom has a nucleus which is made of protons and neutrons, and around the nucleus you have some electrons orbiting. I'm speaking now about the nuclei because there were no atoms at that moment in the universe because the energy was too high, and I'm speaking only about nuclei. And when you have a proton, isolated neutron, this is in fact the nucleus of the more simple atom, which is a hydrogen atom. Probably you know that. So at that moment you had only hydrogen atom. And after 3 minutes around after the Planck era, there are some nuclei which begin to link together to form very elementary nuclei of deuterium. A nucleus of deuterium is just the association of a proton and a neutron. It is an isotope of the hydrogen atom because you have only one proton which is linked to a neutron, and also nuclei of helium which are 2 neutrons and 2 protons. And this is called primordial nucleosynthesis. And after that primordial nucleosynthesis, you have in the universe not only protons, which are hydrogen nuclei, but you have also deuterium nuclei and helium nuclei. And in the years 1940, when people began to ask the question of the origin of all chemical elements in the universe, they had the idea that perhaps in this condition of the primordial universe, when all the matter was very dense and was very hot, this could have been the origin of all chemical elements by nuclear reactions. Because dense and hot, they are the good conditions for nuclear reactions. So why not think that all chemical elements could have been synthesized in the primordial universe? And this was the first idea. And after more calculations, mainly by George Gamow, which were coming from Russia and worked in the United States in this year, it was shown that in this condition, only because the universe was expanding, only the lightest elements, I mean deuterium and helium, could have been synthesized, and later it was understood that the other elements have been synthesized much later by the nuclear reactions in the core of stars, and Nicolas will speak about that probably in a moment. So what is important is that if you make calculation in the frame of this Big Bang models, at the time in the 1940s, they were not called Big Bang models, they were called hot universe models. And Lemaitre, when he was giving the first idea of this model, called that the primordial atom models, and they became called the Big Bang models only, I think, in the 1960s or something like that. And this was very important because this calculation brought the first confirmation of the fact that maybe this idea of a hot universe, Big Bang models, was not so stupid, because when they made calculations, they realized that the abundances of deuterium and helium that you could find in the universe were really corresponding of what you can observe in the universe. Because you know that using spectroscopic techniques and looking at the spectral lines in the spectra of some astronomical objects, you are able to know the physical, the chemical composition of these objects. I mean, galaxy, quasar, interstellar, intergalactic clouds, and it was verified with more and more precision that the abundances of deuterium and helium were, first, they were universal, which is a very important point, and secondly, they were in accordance with the prediction of these models. And so this was a first observational confirmation of the validity of these models. So this is a picture of Alexander Friedman, which was another discoverer of the expansion of the universe, because in 1922, before Lemaitre, he had also found the solution of general relativity describing an expanding universe, but he was in Russia and he was not aware of the observation of the expansion, and he was not he found a mathematical solution, but he did not find the adequation with the observation, because he was not aware of the observation. And this is the reason by why these models are now called the Friedman-Lemaitre models. So this is Einstein and Lemaitre. George Gamow, with I mentioned, made the first calculation of primordial nucleosynthesis. Is that showing the abundances of deuterium, helium, and lithium. Also, I did not mention lithium, but this is the diagram more or less showing the adequation between the prediction of the Big Bang models and the observation of these primordial elements. And this was in the years of 1940 and 50. And very soon was coming a new confirmation of the Big Bang models, and this is due to the next step in the chemical evolution. If you remember, after the Planck era, you have first the quark-hadron transitions, then you have primordial nucleosynthesis about 3 minutes later, and few 100,000 years after that, maybe 400,000 years after that, you have a very important event in the history of the universe, which is called recombination. And this is very important. This could be thought as the transition between the primordial universe and the present era. Few 100,000 years before Planck era. And what happened? It happened that the electrons, which were free, will recombine with the protons, and when you combine an electron with a proton, you have a hydrogen atom. So this was the apparition of the first atom. And this has very important consequences, because when you have free electrons and free protons, this means that the matter is ionized. But when you have hydrogen atom, the matter is neutral. So when you have this recombination, electrons with protons, the universe, which was ionized, is becoming neutral. And the universe at that epoch is full of radiation, of electromagnetic radiation, because the universe is hot, and you know from the physical laws of physics that when a body, any body is hot, it is in equilibrium with radiation. So at that time, the universe was
very hot and in equilibrium with electromagnetic radiation about more or less infrared or optical radiation. But the point was that when the universe was ionized before recombination, the ionization implies that you have a physical link between electromagnetic radiation and matter, ionized matter. So matter and radiation during the ionized era are completely linked together. They cannot move independently. And maybe you know that the radiation, electromagnetic radiation, has a very strong pressure. And this pressure prevents any possibility of contraction. And so during this period before the recombination, the matter has no possibility to contract and, for instance, to form objects like galaxies or things like that. But after the recombination, after the material content becomes neutral, this means that matter and radiation are no more coupled. And this is the reason why this recombination moment is also called the decoupling, because you have a dynamical decoupling between radiation and matter. And this means that radiation and matter will now have two different stories. And the stories of matter is very important, because now you don't have the pressure of the radiation, and the matter has the possibility to condense itself under the influence of its own gravitation. This is called gravitational instability, and this will give rise to the formation of galaxies, clusters of galaxies, stars, and so on, and all the matter, all the structure objects that we know. So this is very important, of course. And on the other side, radiation also is free. And the radiation which was present at that moment, this is about 13 billion years in the past, will continue to be present and to propagate in the universe almost without interaction with anything. And we will observe it exactly as it was at that moment of recombination, 13 billion years ago. The only difference is that due to the expansion of the universe, it is cooled. It was at a wavelength which was in the optical part of the spectrum. Now it is in the millimeter wavelengths range of the spectrum, millimetric radiation. But except that cooling of the radiation, it preserves all its characteristics. And in the years 1940s, this radiation, the presence of this radiation that we could observe now, was predicted by Gamow and collaborators. And after a long story, about 20 years later, it was observed more or less by chance, by two radio astronomers, Penzias and Wilson, which got the Nobel Prize for that. And in fact, they detected this millimetric radiation in the sky, which was isotropic, which was with the thermal spectrum. And the only explanation for that radiation was precisely that I gave from the Big Bang. So we observe some radiation in the millimetric range, which comes about unaltered from that period, 13 billion years in the past. And the only fact that we could observe that radiation was a very strong argument for the Big Bang models, because since 1965, the moment where that radiation was observed, nobody could find another explanation for the presence of this radiation. And after time, with many kind of observation, with telescope, balloons, rockets, satellites, interferometers, and so on, we add more and more information concerning that radiation, about the spectrum, its spectrum, which is very, very conformal to a thermal spectrum, a black body spectrum, about its isotropy on the sky, about its polarization, and every time you get more details, this is more and more in accordance with the prediction of the Big Bang models. So this is really the observation of this radiation which is the best confirmation of the idea of the Big Bang models. Not the only one, but the best one with a very high precision. And this is not only a confirmation of the models, but this gives you very directly information about this past situation of the universe 13 billion years ago. See, this is like a fossil of the universe as that primordial period, so this is very important. And also, since the origin of this radiation is so far away in the past, this is also far away in distance because of the finite velocity of light. This means that sometimes this radiation could encounter some matter between its emission and now, and also we have information about all the matter on the trajectory of this radiation. So this is a very important tool for the exploration of the universe. I will not go, of course, into the details, but observation of this microwave cosmic radiation is a very important subject in cosmology, which allows a lot of which gives you a lot of information about the primordial universe. So about 300,000 years after the Planck era, we have this recombination between electrons and protons, creating the first hydrogen atoms, which has for consequence the decoupling between matter and radiation. Radiation will be preserved, and we observe it now as the cosmic microwave radiation. It is cooled, but it retains many information from that period. And matter, which is free to condense, will beginning this long contraction, which is called gravitational instability, because the idea is that, well, matter is basically uniform at that moment, uniform with a precision of 10 to the minus 5, 10 millions, which is a very strong homogeneity, but not completely uniform. You have the small fluctuations, 10 minus 5. This means that you have some regions where the matter is little more dense than in the neighborhood. And so if it is little more dense, it will feel little excess of gravitation, and so the surdensity will grow and grow and grow and grow more and more, and this is called gravitational instability. And at some moment this will become denser and denser and very dense, and we could follow that following the equation of gravitation self-interaction, and at some moment this will become very dense, so dense that nuclear reactions will be ignited in the core of that collapsing region, and this will mean that a star is born. And this is the process of star birth. And by this process, you will have star formation, condensation of the stars in galaxies and clusters of galaxies. We don't know precisely what form first. First star formation and then star collapsing, stars gathering to form galaxies, or first formation of very large concentration and then stars taking birth inside these fluctuations. But we don't know all details of that because this is a very complicated process. But we know that with a time scale of about 1 billion years, stars, galaxies, galaxy cluster were forming with that time scale, and at some moment our present galaxy was forming into that process. We don't know exactly when. Maybe Nicolas knows more precisely what's the time of the birth of our own galaxy, the Milky Way. But anyway, we have now these hierarchical structures of stars and stellar systems with planets inside galaxies, galaxies inside groups and clusters of galaxies, and clusters of galaxies themselves inside bigger structures which are supercluster filaments. And in the last years we had many papers indicating exploration of the universe at very large scale of hundreds of megaparsec. A megaparsec is 1 million parsec. A parsec is a unit of length used by astronomers, which is about 3 light years. A light year is the distance that light parcours by light during 1 year. So I'm speaking about scales of hundreds of millions of parsecs, and this is about the size above which you can consider the universe as homogeneous. If you remember in the beginning, I mentioned you that when you are constructing a cosmological model, you are assuming that the universe is homogeneous. Of course, at the scale of this room, for instance, it is not homogeneous, because here it is almost empty and here is more dense. But if you smooth the universe at a scale which is larger than planets and stars and galaxies and clusters of galaxies, you should think that it is homogeneous. And this scale is about few hundred of megaparsecs, few hundred of millions of light years. And it is very difficult to explore the real structures of the universe at these large scales. And there are presently some discussions between cosmologists and astronomers if really at this large scale you can consider the universe as homogeneous or not, because you have still big filaments, big voids. So it is not completely clear if the universe is really homogeneous or not at the very large scale. But the main agreement is that it is really, but this is still under discussions. This is a diagram in space-time, and we are here, we are observers. And when you go in these directions, you go far away in distance and you go far away in time, because when you are observing using electromagnetic radiation, and since electromagnetic radiation goes at the finite velocity of light, this means that if you are observing at a distance of, say, 1 million light years, you are observing something which happened 1 million years in the past. So when you go there, you go far away in space and you go far away in time. So there is some kind of limit here, which is a Planck era, and nothing is visible here. And here you have the primordial universe. So this is not a linear time scale. So you go further in time. This is the period of decoupling and of recombination. And the nucleosynthesis that I mentioned is near from the Planck era, 3 minutes only, so it's somewhere like here. So here you have ionized matter before the decoupling, as I told you. So before the decoupling, in that primordial era, matter is ionized. You have protons and electrons which are separated. And after the decoupling, they become neutral. And when you have electromagnetic radiation in the primordial universe, the universe is full of electromagnetic radiation, the red line. But since the material content is ionized, this means that the photons of the electromagnetic radiation are completely diffused by the ionized matter. So they have a very small mean free path. This means that if you have some light, some photon, it will go in all directions. And this means that the universe at that moment is not transparent. It is opaque. This is like some kind of fog, and this is like the interior of the sun. The interior of the sun is completely full of electromagnetic radiation, of photons, but you cannot see in the interior of the sun because you have always diffusion of these photons with the ionized matter of the sun. And this is the same here. The universe is opaque, is transparent, and the universe is becoming transparent at that moment of decoupling, which means that the photon could go in straight line from that moment up to now. And this is called sometimes the moment of last diffusion. And the virtual surface corresponding to that, the surface which is illustrated like that in the picture of the cosmic microwave radiation, is called the last diffusion surface, because this represents the moment, the last moment where the photons diffuse with the ionized matter. After decoupling, the photons do not diffuse with matter because matter had become neutral. So this is the thermal spectrum of the microwave background radiation, and this was observed by the satellite Kobe, which showed with a very high precision that the spectrum is thermal. And this is a theoretical curve, but in fact observations are also present, and the error bars of the observations are smaller than the widths of the theoretical curve, so they are not plotted here. This is a very incredible precision in the observations and a very strong confirmation of the Big Bang models, because the Big Bang models are telling you that this radiation should have been emitted when the universe was in thermal equilibrium. And this curve is really characteristic of thermal equilibrium. So this is a very important confirmation of the Big Bang idea. And this is a map. This is in fact quite old. This could have been Kobe, and now we have much better maps. Maps of how this radiation is appearing to us in the sky. This is not primordial because this is the influence of the plane of our galaxies, which has been subtracted from the data, but this is really cosmological information. And you see that you have fluctuations, and this fluctuation, they are at a level of this -5. So they have been amplified a lot in the picture. And in fact, it is very important to observe this fluctuation because they are due to the very small fluctuation of density which were present in the universe at that moment. And as I mentioned you, the recombination was the beginning of the gravitational instability, which is the growth of the fluctuation under the influence of their own gravitation. But that initial fluctuation, they should have been present, and in fact they are present, they are here. And this picture is very important because this was the first detection of the presence of these initial fluctuations, which are in some sense the germs, the seeds for the galaxies, stars, galaxy cluster, and so on. So it was very important to observe these primordial fluctuations in the microwave background, and this picture was at the origin of the Nobel Prize for the Kobe satellite to matter and smooth. The year of this observation was, I think, around the year 2000. So this is W map. This is more precise maps of this cosmic microwave background, giving more information. So you have information about these initial fluctuations, which will later become galaxies, stars, galaxy cluster, and so on. But you have also a lot of information about the geometry of the universe. And this is giving you information concerning the rate of the expansion, the acceleration of the expansion, the present density of the universe, the contribution of the usual baryonic matter to the present density of the universe. This is giving you a lot of information about the geometry of the universe. So this is one of the last maps of this primordial radiation given by the satellite WMAP, and also this has given a lot of information. Well, I think you are not so interested in the detail. There is a very important point, is that when you analyze this fluctuation, you will not analyze precisely any part of the sky, but you will make some statistics about the distribution of these fluctuations, about their intensity as a function of their angular sky, going for a few arc minutes or arc seconds to the whole size of the sky. And the Big Bang models predict very precise statistics given by these curves. And here you have the data points compared to the curve, and you have a very good agreement. And now with the new observation of the Planck satellite, really the agreement is much better, and this is also a very good confirmation of the Big Bang models and of ideas about the gravitational instability and the formation of stars and galaxies. And this is a picture of the Planck satellite, which gave us the last information concerning all this radiation. Just to show you what is the appearance of a galaxy. This galaxy is not exactly similar to our own galaxies, but the idea is that every luminous point here is a star, and you have about 200 billion stars in a galaxy like our own, the Milky Way, and one of the stars is the Sun with the planets that you know around it. And galaxies like that, they form clusters, and one of the well-known clusters of galaxies is a Coma cluster of galaxies, quite far away from us, about 100 of megaparsecs distance from us. And of course the sky, the space-time is full of galaxies which are organized in clusters and also supercluster. And this is an appearance of the projected distribution of galaxies under the sky, and each point is in fact a galaxy. This means that each point is a cluster of about 200 billion stars. So each point represents 200 billion stars, and this is only a distribution of one part of the galaxy, the more bright galaxy the brightest galaxy we can observe, under a part of the sky. So we have billions and billions of galaxies, each galaxy with billions of stars, hundreds of billions of stars inside it. So this makes probably a lot of planets, of course. So astronomers and cosmologists are very interested in the reconstitution of the distribution in 3 dimensions of the galaxies in the universe, because this is full of information, but of course I would not go into the details. And in fact they are trying to have an idea of this distribution from the observation, and they make a simulation of the process, and of course they compare the observation to their simulation, and the statistics of the distribution of the galaxies is expressed by a power spectrum that you can predict from the theory, and that you can also observe from observation of galaxies with telescopes. And you have also a quite good agreement, as you see. And just to mention another tool to observe the universe, which is gravitational lensing, I will only give you the principle. The principle is that you are an observer on Earth, and you observe a distant object, very distant object like a quasar, but between the quasar and you, the space-time is curved. and for instance it could be curved with a high intensity because you have a massive object, and the gravitation generated by the mass of this object will imprint a strong curvature of space-time. This means that if you have a strong curvature of space-time, the light rays are curved themselves, and the curvature could be such that from the quasar, from the distant luminous source to you, you can have two light rays arriving here. But this means that if you have a light ray arriving you in that direction, you see the object in that direction. So the real object is here, but you see an image of the object here. And since you have another ray, you see another image here. This means that you have situations where you have a unique object and you have two images. Phantom images, if you want, ghost images. And this was first observed some decades ago, and this was the double quasar. And in fact, two quasars were apparently observed very near from each other, few arc seconds, with similar characteristics. And after years of observations, it was confirmed that there were in fact two images of the same quasar by the effect of gravitational lensing. And this effect of gravitational lensing, which is a direct manifestation of the curvature of the universe, can generate multiple images, but can also generate amplification, deformation, and this has become a very efficient tool for the exploration of the universe, because if, for instance, you observe two images or more images or a deformed image or amplified image, this gives you a lot of information about the curvature of space-time between the distant source and you. But if you have information about the curvature of space-time, this means that you have information about the mass distribution, which is the cause of this curvature of space-time. And this allows you to explore the mass distribution between the distant source and you, even if you have no light, if you have no visible objects. And this allows you an exploration of what is called the dark matter, the invisible mass. And you know that presently astronomers and cosmologists are thinking that beside the mass that we can know that we see in the object, like stars, galaxies, also planets, we have a lot of what is called dark matter, a lot of massive objects which are for some reason not visible, but we feel their gravitational attraction. We can see their gravitational attraction. And with this kind of effects, we can explore the mass distribution between the distant object and us, and it has absolutely no importance if this mass is visible or not, because it has exactly the same effect on the bending of the light rays coming from distant sources. So this gravitational lensing has become a very powerful tool for the exploration of the universe. For instance, this picture, all these arcs are images of the same galaxies. So you have somewhere in that direction a very distant galaxy, which is almost spherical, but the light rays coming from that very distant galaxies are deformed, are curved by the mass distribution corresponding to that cluster of galaxies. And from that unique galaxy, which is very far away and which is circular, you see a multiplication of images which are completely deformed and amplified, giving this arc distribution. So each of these is a ghost image of a unique object which is almost spherical and which is very far away. And when you analyze such a picture, you have a lot of information about the mass distribution between that very distant galaxy and us. This is a very powerful tool of exploration. Okay, I will stop here. And we know quite a lot about the evolution of the universe, to conclude, between the Planck time and now, but not so much, in fact, because concerning the primordial universe, as I told you, if I go back in time, we are in the present state, and we know, for instance, that 4.5 billion years ago was the formation of the solar system and of our planet. Some billion years before that was the formation of our galaxy, and some billion years before that was the recombination. The recombination is the period, is the beginning of the period where we have galaxy formation, and we understand that quite well. Before that, this is the primordial universe. And in the primordial universe, at the recombination, for instance, the universe was 10 times hotter than now. This means that everywhere in the universe at that moment, the temperature was higher than 3,000 degrees. At that time, it was no part anywhere in the universe, no place where the temperature was less than 3,000 degrees. And it was no place where the density was less than 1 billion times the present density of the universe. So the universe was much denser and much hotter. And if you go further in the past, still denser and still hotter. And when you go further and further, of course the physics is becoming more and more different from the present physics. And at that time, it is governed by electromagnetic interactions. When you have the recombination of electrons and protons, the emission, the diffusion of electromagnetic radiations, this is electromagnetic physics. When you go further in the past, this is atomic physics. When you go any further, nuclear physics, primordial nucleosynthesis. When you go any further, this is particle physics. But particle physics, at this very high energy and temperature, we don't know it very well. We have some information because we can test some very peculiar situations in the big accelerators like the LHC in CERN, but only partial information. And at this moment, we don't really know what happened in the primordial universe. This means that even after the Planck era is completely unknown. We know about nothing about it. But even after the Planck era, the physics is very uncertain. Maybe we have some phase transition. Maybe we have the physics governed by a grand unified theory that we still don't know. Maybe we have some process which is called inflation. Probably we have at that moment the generation of the initial fluctuation which were present at the recombination, and after that gave rise to galaxies and galaxy cluster and so on. But the further we know in the past, the greater is our uncertainty. So the conclusion is that we have quite a good knowledge of some part of the history, and with a very high precision. And it is often said that now cosmology became high precision observatory sciences. Well, this is true for some part, but of course there are a lot of mysteries, and about these mysteries, the presence of dark matter, because we don't observe this dark matter, and it should be here. And if it is not here, what is there to explain all the phenomena we observe in the kinematics of galaxies, clusters of galaxies, in gravitational sync? We don't understand also why the expansion of the universe is accelerating. Maybe it's a dark energy, as pretend some physicists. Maybe it's a cosmological constant. We don't know. We don't know a lot about the primordial universe. So we have a good picture of the evolution of universe and the moment and the conditions in which galaxies and stars appeared. But the cosmology is still full of mysteries, and these mysteries are not completely mysteries of cosmology, but in fact they are mysteries of physics, because why we don't understand primordial universe? Because we don't have a good theory in physics which can account both for gravitation and quantum physics. So this is a limitation not of cosmology but our physics. What is dark matter? We don't know, because we don't know anything in physics which can do the job. And if we discover dark matter, this means that we discover new physics. What is accelerating universe? We don't know. People are speaking about dark energy or something like that. We don't know. But if dark energy exists, this means that our physics is not the right one, because in our physics, our present physics is incompatible with dark energy. So if we discover something like that, this means that our physics has been changed. And the conclusion of that is that, in fact, we know better our cosmology, we have a better knowledge of the Big Bang model than of our physical theories. We are more secure about our cosmology than of our theoretical physics. And I think this is nice for cosmology, but we still have a lot of work. Thank you.